Hey guys, so in this video we will be going over the balanced binary tree LeetCode problem in Python. So this problem deals with height. So if you don't understand that concept quite yet, check out the video in the description below, which briefly goes over the difference between height and depth in a binary tree. And they're both very important concepts to understand. So in this example that we're given here, we have a tree where 3 is the root, 15 and 7 are leaf nodes, and 9 is a leaf node as well. So in order to determine why this is actually true in terms of height, we have to find the individual heights of each node. So 7 is a leaf node, 15 is a leaf node, and 9 is a leaf node. So they automatically have heights of 0, 0, and 0. 20 is 1 above 0, and mathematically we can find its height by saying 1 plus max of left height and right height. And left height for 20 is 0, since left node is 15, which has height of 0, and right node has a right height of 0. So 20's left height is 0, right height is 0. Max of 0 and 0 is 0, so 0 plus 1 is 1. And then finally 3, using the same mathematical formula, max of 0 and 1 is 1, 1 plus 1 is 2. So 3 has a height of 2. Now in this situation, this binary tree is height balanced because when comparing two nodes, specifically one left and one right node of any node in this binary tree, their difference is not greater than 1. So in other words, left height minus right height, and the absolute value of this, because right height could be greater than left height and vice versa, so both have to be accounted for, is greater than 1. So if it's greater than 1, then this binary tree is false. But since any two children nodes, their difference is not greater than 1, we can say that this binary tree is true. So for example, 15 and 7, left height is 0, right height is 0, 0 minus 0 is 0, and since 0 is not greater than 1, it's true. 20's height is 1, 9's height is 0. Absolute value of left height minus right height is 0 minus 1, which is negative 1. Absolute value of negative 1 is 1, and 1 is not greater than 1, so that's true. And then finally, that's the last step, and we finally proven that this binary tree is true. Now let's go over a situation where we will return false for a binary tree because it's not height balanced. As you can see, I already wrote out the heights of each node, and you can see that 3 has a height of 2, whereas 4 has a height of 0. Now, the absolute value of the difference between the left and right nodes of 8 are 2 minus 0, which is 2. 2 is actually greater than 1, so this binary tree is not height balanced. It is false. And this is only because these two nodes have a difference of height greater than 1, which makes this whole tree false. So that's an example of a binary tree who will output false when going through the algorithm. So in order to really get into how we have to implement this, we have to understand a couple of things. And we have to be able to look at very specific tasks we need to accomplish in order to get this algorithm to work. First of all, we need to find the heights of each and every node in the binary tree. This is important because in order to determine if a binary tree is true or false, we have to know that every child node when compared to the other child node is always going to be less than 1 when finding the absolute value of their difference. So in this situation, 2 and 0, 2 minus 0 is 2, and 2 is greater than 1, so we found that this binary tree is false. The second thing we have to know is what type of traversal pattern this is, and we're going to explain this in a different video, which I'll link in the description below, if you don't understand what pre-order, in-order, and post-order are. But basically, these are different ways of traversing a linked list. And this is important because when we're applying a recursive algorithm to this binary tree, we have to know what order the nodes are traversed. The second thing we need to know is we have to find the difference in height for each left and right subtree for each and every node. So given a node like this, we have to know its left and right subtree as well as its difference, because the difference will judge if the node is balanced, height balanced or not. We also, this is a very important one, we need a condition that handles when a node has no left or right subtree. So basically when we're visiting a leaf node, and we have to have this in code where we understand when we traverse this binary tree, when we visit 9, which is a leaf node, we have to have some way of understanding that this is a leaf node in code, and we're going to show you how to do that shortly. Another thing is we have to be able to output false for the entire binary tree when one or more instances of nodes have a height that's greater than 1. And yeah, that's pretty much it. Those are the only conditions we have to account for. So let's go into the traversal. This is going to be a post-order traversal because we visit the root node last. So we're going to start by visiting 3 first. So let me write the order. 3 will be visited first, and orange equals order of nodes traversed. So 3 is going to be visited first, then 6, and then we go up to 3 and down to 2, and then 19 is finally traversed. So that's the left subtree. We visited the left subtree, and now we have to visit the right subtree. So 4 will be visited, so that's 5, and then finally 8 is the root node, so it's going to be visited last. So this is the post-order traversal, and this is what our code will be doing when finding the height for each individual node. So how do we recursively iterate through a binary tree? Well, this is like the meat of the recursion, the problem, because we are finding a recursive solution for being able to iterate through the binary tree. So as you can see, this function definition is recursive because the function's body also has this function definition within it, which means that this definition will run multiple times until we reach a certain returns value, and at which point this statement ends. So let's do an example of this where we look at the binary tree and we see what's actually happening with left height and right height. And I created a separate one. So we have the binary tree, and we're trying to find the left height and right height of 8, which is the root node. This is the very first node that we are looking at in this binary tree. Now left height equals check root.left. Root.left is 3. So this will be substituted for 3. And before we even visit this statement, we have to be able to do something with this. So what is check of 3 or node 3? Well, we can't really assign anything to left height because there's no return value. The only return value statement we have here is return -1 if root is none. And root isn't none. Root is actually 3. So we can't really do anything. So because of that, we have to look at this statement one more time and actually take it a step further and define left height again. But instead of root.left, 3, which was root.left, is now the root statement. So we're actually looking at the check function definition again, with root.left being root now. So now we're at 3. So left height is 6. Well, it's not 6, but check root.left is 6, and we're trying to get the return value of check 6. Well, we can't really do anything because 6 isn't none. So we go a step further again, and we make 6 the root statement. So this def check root is this statement, and this def check root is this statement. That's basically what's happening. And what we're doing is we're recursively running the check root function until something happens. So at this stage, we can say that left height equals check root.left. Root.left, at this point where root is 6, we can say that root.left is null. There's nothing here. And because there's nothing here, we can actually run this statement, which says if root equals none, we return -1. So root.left is none, and because of that, we can say that left height is finally equal to -1. So left height is now -1 at this point because it's none. So we have something here, and we can also, now that we have -1 defined to be left height, we can finally move on and look at right height. And right height is also -1 because the right child node of 6 is also null. So we can assign right height to -1 as well. And that's the most we can do as of now with the statement that we're given, because we only have the condition where we do something if root equals none. So I kind of created a visualization for this where blue represents we haven't really done anything with this, and pink is the iteration process that goes on immediately after due to left height. And then this statement runs in green because it doesn't work. Okay, so now that we have this in place, we can move further and explore what happens when we don't have a leaf node. In other words, what do we do, or how do we compute the height if the node isn't 6? And we do this by running the formula for finding height, which is 1 plus max of left height and right height. And what we can do is we can actually return this and put this within the check function, so that after we identify that a specific node is not a leaf node, we can run this statement next. And I actually do that here. So after finding that root is none, we can finally run this return statement. And let's go back to the example we made and explore how we do that. So we can add return 1 plus max of left height, which is this, and right height. Let me remove some of these arrows. So now that we have this statement, we can go back to where we were with defining left height and right height as -1 and -1. And now that these two return values have actual values assigned to them, we can use this return statement, and we can actually find the height of 6. And we can do this because left height and right height, which are the only variables in this statement, are defined as -1 and -1. And this statement will, this I guess iteration that we're doing right now is only applying to 6 right now. So we're only working on node 6. So check root is return 1 plus whatever max, and this value, this return statement will output 1 plus -1, since -1 is maximum of -1 and -1, which equals 0. So we're able to find the value of this left height to be 0. And we were able to do this because this function definition is basically this statement, because we're going a step into it. So now left height, let me make a different color, will return 0 because left height is -1 and right height is -1 for this node. Okay, so now that we have left height defined as 0, we can move to looking at this one, this right height statement, because we've already been able to find left height and right height, but we haven't been able, and we've been able to find left height for the node 3, so this one. Node 3's left height is 0, but we haven't been able to find the height of 2. So that's what we're going to do now. So this right height, let's copy and paste the function definition, and let's make it so that we're now looking at, okay, so now we're going to check for root, check root where root is equal to 2. So as you can see, 2 is right here, and its left node is 19 and its right node is none. So we can say left height is equal to check root.left. Root.left is node 19, and since it's not none, we can't return a value for left height. So we delve into left height again by creating a check root statement with 19 being the root. And finally, from 19, we can see that left height and right height are none and none. So we can return -1 due to this return statement. So we have left height equal to -1 and right height also equal to -1. So we have these values defined for when check root is on 19, so when check root is on this node. So we can finally continue on with this statement, and we see that return 1 plus max left height, right height. We have left height and right height defined to be -1 and -1. So we can return 1 plus max of -1 and -1, which is -1, equals 0. So we have that node 19 has a height of 0 because we return 0 for that node. So 19 has a height of 0, and we can finally call left height and say that it has a height of 0 for when check is on 2. So when check is right here, we finally found that left height is 0. So now that we found left height, we can move down to right height. Right height is equal to -1 because the root node of root.right is nothing, none. So therefore, check of none equals return -1. So right height has a height of -1. So this is -1. And now that we have left height and right height defined as 0 and -1 respectively for node 2, so we're on this node right now, we can finally return a statement for this node, which is left height is of height 0 and right height is of height -1. 1 plus max of 0 and -1, max of 0 and -1 is 0, so 1 plus 0 is 1. So this has a height of 1. So this is 1. So now we can actually go up now that we know that node 6 has a height of 0 and node 2 has a height of 1. We can go back up to the node 3, and we can fill in this right height, which is now going to be 1, because right height for node 3 is the regular check node for node 2. So now we can apply the 1 plus max formula for node 3, which is 1 plus max left height, right height, and we return this. So this would be 1 plus max of 0 and 1 is 1, so 1 plus 1 is 2. So we have node 3 with a height of 2, and we can, now that we finished node 3, we can finally go back up to the main check that we started with, and we can say that left height has a height of 2, return of 2. Now we can go to right height, and notice that at this point we've finished the left subtree, and since this is a post-order traversal, we're now going to go to the right of the root, which is going to be right height, and finally we're going to visit 8 last. So let's go through that right now. So right height equals root.right equals 4, and let me copy and paste this above because we have more room, and we see that root.right, which was originally 4, is now going to be root, because we're now looking at, let me change colors, we're now looking at 4, so root is now 4. And left height, and this should be obvious from the previous examples, left height is none, right height is none, so left height is -1, right height is -1 because of this statement. And we can finally, since we know left height and right height, we can create a return statement. So 1 plus max of -1 and -1 is -1. 1 plus -1 is 0. So 4 has a height of 0. So now that we've found the return value for this node, we can put that for right height of 8. And we have left height and right height defined, so we can finally do 1 plus max of left height, which is 2, right height, which is 0, is 1 plus 2 is 3. And we've successfully found the height of each and every node by using this simple recursive formula. So we've been able to show that we can write this recursive formula for finding the height of each and every node in this binary tree, but we haven't really gotten to the main problem and solution that needs to be solved, which is how do we show that this binary tree is balanced or not. And first of all, we have to determine if it actually is balanced or not, and we can say that it's not because there are 2 children nodes of a node, and a node is node 3, and the 2 children nodes are, or sorry, not node 3, but node 8, and the 2 children nodes are node 3 and node 4, and they have heights of 2 and 0 respectively. So a binary tree is height balanced if the difference between the absolute value of the difference between 2 children nodes in any node is not greater than 1. So absolute value of 2 minus 0 should not be greater than 1 if it's to be balanced. And it is. 2 is greater than 1. So we can say that this tree is not height balanced. And we need some way to signify that within this code. And how we can do this is by creating a if statement within this recursive formula. So let me write one right here. And it'll occur right before we calculate the height, where we say if absolute value of left height minus right height is greater than 1, we return -2. This number can be anything. It could be -3, it could be -8, negative whatever. As long as it doesn't get in the way of the return values, the possible return values for this, or it's not -1. So a good bet is not making it positive and just making it a number less than -1, because there's no way you can attain it. So we return -2 if the height difference is not balanced. So from this example, we can go back to when we checked for the right height and left height of node 8, node 8 being this node. And we can say that we can put this statement in between 1 plus max and the root equals none statements, so that if this actually is not balanced, we don't run this statement anymore, right? Because we have to find if it's imbalanced before we actually determine the height. If it is balanced, we do determine the height, but we need to have this condition run first. So if absolute value of left height, and we're talking about node 8, if absolute value of left height, which is 2, and right height, which is 0, referring to nodes 3 and 4 respectively, is greater than 1, return -2. So 2 minus 0 is 2, 2 is greater than 1, so we return -2. So instead of returning 3 for 8, we return -2. And this shows that this binary tree is in fact not balanced, because we show that -2 is the return value for the whole tree. So we need some way to resemble this. So we say outside of the function definition, we have a return statement that says return return check root if it's not equal to -2. So this is basically saying if check root is not equal to -2, return false, else return true. So this is just a much easier and more succinct way of writing this same statement. So this statement will, this whole thing will be within another function definition. So we can call it def balanced func whatever parameters, and this whole thing will be returning from this statement, return false, since check root is equal to -2. And that's pretty much the gist of it, except for one more element, which is the fact that this binary tree doesn't account for circumstances where -2 occurs in, let's say, for example, 6 and 2. So say 6 and 2 are -2, then yeah, we say that we return -2 for this statement, but that -2 doesn't get transferred all the way up to the root. And we need some way to show that if two child nodes, are imbalanced in any part of the binary tree and not just in the direct children of the root node, that the whole thing is false. And we do that by adding an additional if condition. If absolute value of left height minus right height is greater than 1, or left height is equal to -2, or right height is equal to -2, then we return -2. And that handles all the situations where we have unbalanced nodes in the lower parts of the binary tree. And that's pretty much it. We've successfully been able to implement code that recognizes whether a binary tree is imbalanced or not, and returns true or false depending on whether -2 is outputted from the root or not. And that's it for the video. This is I think this is the first video in the series of binary trees that I've done. So if you like this, please let me know. If you have any comments or concerns, let me know. I feel like I explained these very, very slowly, but I want to get as many concepts understood, and I want to make them as easy as possible. So I feel like I have to sacrifice speed for just reiterating myself 100 times. So let me know if you'd like a more quicker way of solving these problems. But let me know how your data structure journey goes, and hope to see you all in the next video. Peace.